All right, let's talk about limits. um, limits are going to be useful for us throughout this course, and there's something that you'll talk about a lot in calculus. We're not really interested in getting a really deep understanding of limits here. I'm more interested in just getting the intuition behind it, because it's going to be useful for us in this course. And because there's some algebra involved in calculating limits that I would like for you to practice before you move on to calculus. So here's the notation. The statement limit as x approaches c of f of x equals L means that as x gets closer to c, f of x is going to get closer to L. All right? To give you an example of this idea, let's take a look at these two functions. So they're pretty much identical, except that g of x has a little piece missing at x equals 4, and instead the function value at x equals 4 is 2. So what the concept of the limit is trying to capture is that the function value may not be the value that you sort of expect the function to approach, right? Like if you're looking at this function, then you expect the function value to be 5, right? As x approaches 4, you're approaching y equals 5. But that's not what the function value actually is, right? So the idea behind the limit is what value are we getting closer and closer to, right? Not what is the actual function value, but what value are we getting closer and closer to. So note that when you're looking at f, the function value, f of 4 equals 5, and the limit as x approaches 4 also equals 5. So the limit and the function value are the same thing. But with g, that's not the case, right? The limit as x approaches 4 is 5, but g of 4 is 2. Okay? So it's important to keep that distinction in mind. When we're trying to determine what the limit of a function is graphically, we look at both what value we're approaching from the left and what value we're approaching from the right. So using this function as an example, so we have this weird kind of piecewise defined function, right? Well, as we approach x equals 2 from the left, we're approaching y equals 1. As we approach x equals 2 from the right, we're approaching y equals 4. Okay. The way that we write this down in math symbols is as follows. So we would say limit as x approaches 2 from the left, right? So if you have a little negative sign written as a superscript next to the 2, that means that you're approaching from the left. You're approaching from the negative direction, right? So limit as x approaches 2 from the left is equal to 1. In a similar way, this one means limit as x approaches 2 from the right, right? So the limit as x approaches 2 from the positive direction. So as we approach from the right, the function value that we're approaching is 4. Now, since we're approaching two different values as we approach from those directions, we say that the limit does not exist, okay? So sometimes the limit doesn't exist for certain functions, and this is one of them. And this is just a GIF of Lindsay Lohan and Mean Girls saying the limit does not exist, which if you haven't seen that movie, you should. It's a good one. But okay, let me give you a few examples. So let's use the graph to find the following limits. So let's find the limit as x approaches 1. So as x approaches 1 from the left, y is approaching 1 as well. As x approaches 1 from the right, y is approaching 1. So you're approaching 1 from the same, or from both directions, you're approaching y equals 1. So that would be the limit as x approaches 1. If we look for the limit as x approaches 3 from the left, it seems like you're approaching y equals 5. From the right, again, it looks like you're approaching y equals 5. So the limit as x approaches -3 is 5. But now let's look at the limit as x approaches -1. as you approach -1 from the left, so as you approach x equals -1 from the left, you're approaching y equals +1. As you approach x equals -1 from the right, you're approaching y equals -1. And since you're approaching two different values from the left and from the right, that means that the limit as x approaches -1 does not exist. I'm just going to use DNE for does not exist. Okay. Now notice that notice how that corresponds to the function values. Okay, so f of 1 is equal to 1. But f of -1, well, f of -1, it almost looks like you have two different options, right? But notice that there's a hole here, right? This is an open circle. So f of -1 does not equal 1. F of -1 equals -1. So what I want to point out there is that even though the limit does not exist, the function value still does. So limits and function values are not necessarily the same thing, right? Here, the limit and the function value were the same, right? Limit as x approached 1 was equal to 1, and f of 1 was equal to 1. So the limit and the function value were the same, but here they're not the same, right? So limits and function values are not necessarily the same thing. Let's do another example. Same limits and function values, but a different function this time. Limit as x approaches 1. From the left and from the right, it looks like we're approaching the same value, and it looks like the value we're approaching is 3. Limit as x approaches -3. From the left and from the right, it looks like we're approaching the same value. That value is 5. Limit as x approaches -1. From the left and from the right, this time it looks like we are approaching the same value. It looks like we're approaching 1. Right? So of course this one is 1 and this one is 1. Now f of 1 is 3. F of -1 is 1. So in this example, the function values match the limits, right? F of 1 is 3, limit as x approaches 1 is 3. F of -1 is 1, limit as x approaches -1 is 1, right? So the function values match their corresponding limits. Okay. That wasn't the case, obviously, with example 1, as we pointed out. But what I want you to do now is take a look at example 3, see if you can work out these limits on your own. Okay. So I'm going to give you my answers now. Limit as x approaches 1 is again 3. Limit as x approaches -3 is again 5. Limit as x approaches -1. As you approach from the left, you're approaching y equals 1. As you approach from the right, y is approaching -1. Or sorry, +1. So I think limit as x approaches -1 is +1, right? But notice this time that f of -1 itself does not exist, right? It's undefined. So this is an example, and maybe let me say f of 1 is again 3, right? So this is an example of something where the limit exists, right? The limit exists, but the function value doesn't. The first example was an example where the limit did not exist, but the function value did. Here, the limit exists, but the function value does not. So the whole moral of the story is that function values and limits are not necessarily the same thing. Oftentimes they go hand in hand, but not always. And by the end of the section, we'll have a better handle on when exactly function values and limits are the same thing and when they're not, okay? But that's kind of the graphical idea, okay? Oh, I wanted to say, sorry, I was getting ahead of myself. So I also wanted to say, we can throw infinity into the mix as well. So in a couple of different ways. So first of all, it could be the case that as x approaches some finite value, your function value is approaching infinity or negative infinity, right? technically we would say that these limits don't exist, but it's pretty common practice to use this notation, right? To say that the limit is infinity or the limit is negative infinity. It's important though that f of x has to approach the same value from both directions in order to say that limit exists. There are details here, right? Details here that I am glossing over big time, but those details are for your calculus instructor to fill in for you. So I'll leave it to your calculus instructor. But what I want to do is I want to use Desmos to graph a couple functions and then use those graphs to determine a couple of limits. So let me show you Desmos in case you're not familiar with it. So you go to desmos.com and then hit start graphing. And it's just an online graphing calculator that's really pretty nice. So I can type in example 4, we want to look at 1 over x squared. So I can type in f of x equals 1 over x squared. And to get the over, I'm just using the little slash on my keyboard. To get x squared, to get that superscript, I'm just using the little caret sign above the 6 on my keyboard. You could also, if you're not familiar with all those shortcuts, you could just say show keypad, and then you could use these buttons and stuff to get all the same thing here. But anyway, here's what our function looks like. This is f of x equals 1 over x squared. And now I want to use this graph to find the limit as x approaches 0. So as x approaches 0 from the left, it looks like f of x is just going off to infinity, right? As x approaches 0 from the right, it looks like f of x is also going off to infinity. So we would say in this case, we would say the limit as x approaches 0 of f of x equals infinity. That's what we would say. So just to draw a quick sketch, right? This is what the function looked like. And so limit as x approaches 0 of 1 over x squared, infinity, right? Number 5 says to use Desmos to graph f of x equals tangent x. We don't even need to use Desmos though. You should know what tangent x looks like based on your experience in trig. You know that it's got to have some asymptotes at negative pi over 2 and at pi over 2. And then it does this thing, right? This is what tangent looks like. And it kind of repeats that over and over and over again, right? If you didn't know this about the tangent function, if you didn't know that this is what tangent looks like, well, then you could take a look at it in Desmos. Okay, we're going to review how to graph functions and stuff a little bit later on in the course, so don't worry about it too much. But this is what it looks like. Notice that as we approach from the left, the function is approaching positive infinity. As we approach from the right, the function is approaching negative infinity. So in this case, we would say that the limit does not exist, right? We could say, of course, we could say limit as x approaches pi over 2 from the left. We could say that's, from the left, we could say it's approaching positive infinity. And we could say, as we approach from the right, it's going down to negative infinity. But then the limit overall doesn't exist because you're going 2 separate directions. Okay? So that's one way that infinity could show up when we're dealing with limits. Another way that infinity could show up is that we could be interested in just knowing what happens as x gets really, really large or really, really small, right? Really large in the negative direction. Okay. So for example, let's use Desmos to graph 2 to the x minus 3. And then let's use that graph to see what the limit as x approaches infinity is and what the limit as x approaches negative infinity is. So let's open up Desmos and see what we've got. So we want to do 2 to the x minus 3. Okay, so this is the function that we're ending up with. The first question we want to answer is, what is the limit as x approaches infinity? In other words, as x gets really, really large, what's happening to this function value? Well, it looks like the larger and larger x gets, the larger and larger the function value gets. It doesn't seem to be approaching any finite value. It seems to just be growing and growing and growing. So, so I think that the limit as x approaches infinity is infinity. In fact, that's what I'm going to write down. But then the next question is, what's the limit as x approaches negative infinity? Right? So as x gets really, really large in the negative direction, what's happening there? So let me go back down. So as x gets really, really large in the negative direction, well, there we have a different story, right? It doesn't seem like this thing keeps getting smaller. And, well, it does keep getting smaller and smaller and smaller, but it doesn't seem like it's ever going to pass whatever this value is. It practically looks like a straight line, right? It doesn't seem like it's ever going to pass it. So this should be -3. In fact, if we plot y equals -3, you see that the graph never goes below that line, right? Here it kind of looks like it is equal to the line, but if you zoom in, eventually you'll see a discrepancy. You have to zoom in kind of far, but there you go. You start to see it, right? So the function never quite reaches -3, but it seems like it's getting closer and closer to it. So we would say that that's the limit, right? So the limit as x approaches negative infinity of this function seems to be -3. Okay. So those are some ways that infinities could pop into the mix, and I just wanted to point those out to you. But all of the work that we've done so far has been like a graphical look at limits. But you don't even need necessarily to look at a graph. It's nice to have a graph, but you don't really even need one. You could just make a table of values, right? And in calculus, you're going to do this pretty often. So let's practice just a little bit. When you make the table, it's important that you make a table approaching from both the left and from the right of the value that you're trying to approach. So this one says, use a table to find the following limits, and then look at the graphs in Desmos to confirm our findings. So let's do that. If we want to find the limit as x approaches 2 of 3 to the x minus 1, then if we're approaching from the left, we can make a table of values. If I'm approaching 2 from the left, that means I'm going to be plugging in values slightly less than 2. So I can maybe start at like 1.5 and then move up a little bit closer to 2, and then a little bit closer, right? And then a little bit closer. And I can keep getting closer and closer to see what value I'm approaching. I'm just going to use my calculator to see what these function values are. So we're going to have 3 times 1.5 squared minus 1. That's 5.75. We could plug in 1.9. And then we get 9.83. Okay, maybe this is going off to infinity. We could plug in 1.99. We get 10.8803. We could plug in 1.999. We get 10.988. Okay, so it seems like the growth is sort of slowing down. Seems like we're getting closer to 11. Let me go one more. This is really close to 2. Let's see what happens. We get 10.9988. So yeah, so I think that what's happening is that we're approaching 11. So as we approach from the left, it seems like we're getting closer and closer to 11. Let's see what happens as we approach from the right. So if we're approaching from the right, that means I should be plugging in numbers slightly bigger than 2. So I might start at like 2.5, and then I might get closer to 2, right? So go down to 2.1, and then closer, and then closer, and then closer. Let's see what we end up with. So if we plug in 2.5, we get 17.75. If we plug in 2.1, we get 12.23. If we plug in 2.01, we get 11.1203. Okay, so it seems like it's getting closer to 11. Here we get 11.012. Here we get 11.0012. So yeah, so it seems like we're approaching 11 again from the right. So there you go. You're approaching the same value from both directions. So this limit, it seems like, is 11. Okay? And so that's how you would use tables to determine what a limit is. Now you might wonder, why don't we just plug in 2 itself and get this over with, right? Because notice that if you plug in 2, you get 2 squared is 4, 4 times 3 is 12, 12 minus 1 is 11, okay? The problem with that is that function values are not necessarily the same thing as limits, right? We saw that on the very first page, okay? The function value here, f of 4, or sorry, g of 4 is 2. But the limit as x approaches 4 is 5. Okay? So limits are not necessarily the same thing as function values. They are sometimes. And we're going to talk, I think on the next page, we're going to talk about when function values are the same thing as limits. But for now, it's not safe to assume that a function value is the same thing as a limit. It just so happens to be the case here, okay? But that's not always the case. Part B is actually a really good example of that. Well, maybe not such a good example. Let's take a look at part B. Notice that if you plug in 3, you're going to get 4 over 0, which is undefined. So is that actually what the limit is? I mean, so in other words, the function value, f of 3, is undefined. But what's the limit, right? The limit could still possibly be a number, right? The limit could still possibly exist. So we make a table of values to find out. So from the left, we'll be plugging in numbers slightly less than 3, like 2.5, and then 2.9, and 2.99, and 2.999. From the right, we'd be plugging in values slightly larger than 3, like maybe 3.5, and then 3.1, and 3.01, 3.001. Let's see what's happening. If you're following along, make sure to put parentheses around these things when you punch it into your calculator. Okay, so I'm going to have 2.5 plus 1 over 2.5 minus 3. I'm getting negative 7. I'm going to replace that with 2.9 instead. We get negative 39. Oh, wow. Okay. Seems like that's exploding. Yeah, negative 399. I suspect this one's going to be negative 3,999. Let me check. Yeah, so this thing, it seems like it's just going off to negative infinity. What about from the right? Is the right also going to explode off to negative infinity, or is it going to do something else? Let's see. It's 3.5. 3.5. Okay, so this one's starting at 9. If I replace it with 3.1, I get 41. If I replace it with 3.01, I get 401. Okay, so then I suspect this one's going to be 4001. But whatever the case, yeah, 4001. Anyway, whatever the case, it's clear that what's happening here is not the same thing as what happened there, right? What's happening here is that this is shooting off to positive infinity. And so since you're approaching 2 different values from either side, I think this limit does not exist. Okay. Anyway, we were supposed to use Desmos to confirm our findings. Let's do that now. So the first function was 3x squared minus 11, or minus 1, sorry, 3x squared minus 1. Oh goodness, where am I? I need to zoom out a bunch. There we go. There we are. Okay, 3x minus 1. And we wanted to look at the limit as x approaches 2. So limit as x approaches 2, as x approaches 2, might be helpful to zoom out some more, I guess. As x approaches 2, it seems like, yeah, it seems like we are approaching 11. So that confirms that suspicion. Let's look at the x plus 1 over x minus 3. We were interested here in the limit as x approaches 3. So maybe let me just put x equals 3 on here so that we can see it. But yeah, limit as x approaches 3 seems like from the left we were going to negative infinity, from the right we were going to positive infinity. That confirms our suspicion for sure. So the limit does not exist in that case. Okay, a couple more of these. This is the same function as before, same function as part B, but now we're looking for the limit as x approaches infinity. When you're approaching infinity, there's no need to approach from two different directions, right? Because in order to approach infinity from the right, you would somehow have to get a number bigger than infinity, which is, of course, impossible, right? So, so we're just gonna, to calculate this limit, we're just gonna plug in bigger and bigger and bigger numbers, okay? So maybe we could plug in 10 and then 100 and then 1,000 and then 10,000 and see what's happening to f of x. So when I plug in 10, I get about, 1.57143. If I plug in 100, then I get about 1.04124. I think it seems like we're probably approaching 1, but let's plug in 1,000. Yeah, if we plug in 1,000, we get 1.00401. And if we plug in 10,000, then we're getting 1.0004. So yeah, I think what's happening is that we're approaching 1. So we would say the limit as x approaches infinity of this thing is 1. And we can see that in Desmos as well, right? As x gets larger and larger and larger and larger, it seems like this value is getting closer and closer and closer to 1, right? So I'm pretty sure that's what's happening. Okay, one more. This one is similar to part B in the sense that if you plug in this number, so if you try to find the function value, you're just going to get an undefined expression. So obviously that's not very helpful. It's much more helpful to make a chart to see what's happening as we get closer and closer to -1 without actually equaling -1 itself. So let's see. Again, this time we're approaching a finite value, so we're going to approach from both the left and from the right. Okay. So from the left, plug in something slightly smaller than -1, like -1.5, and then we'll try to get closer and closer to it. So -1.1, -1.01, -1.001. From the right, we're going to be plugging in values slightly bigger than -1. So something slightly bigger than -1 would be like -0.5. And then we might try to get closer and closer, -0.9, -0.99, -0.999. Let's see what we get. Okay, so I'm going to do negative 1.5 squared minus 1 over negative 1.5 plus 1. Again, remember to use parentheses appropriately, but you get negative 2.5 here. If we replace that with negative 1.1, we get negative 2.1. Replace it with negative 1.01, and we get negative 2.01. Oh, this is interesting. So I suspect that we're going to get negative 2.001, and it seems like the value that we're approaching then is negative 2. So from the left, we're definitely approaching negative 2. What's happening from the right? So if I replace negative 1.001 with negative 0.5, I get negative 1.5. If I replace it with 0.9, then we get negative 1.9. Okay, if I replace it with negative 0.99, we get negative 1.99, and then I suspect that here we would get negative 1.999. And yeah, interestingly enough, we are approaching negative 2 again. So this function value seems to be, or this limit rather, seems to be approaching negative 2. And that's really interesting, right? It's like, so even though the function value itself is undefined, we still have a limit, right? The limit is still negative 2. And we were able to use a chart to verify that. I'm not going to verify this in Desmos, okay? I'm just going to leave it at that. One thing that I'll warn you of when you're looking at charts and graphs and stuff is that you can easily be deceived. For example, we could look at a graph or make a table of values to calculate some kind of limit, and we might think that the limit is 5 because it looks like it's 5 on the graph, or it looks like it's 5 in the charts, when in reality the limit might be something like 4.97, right? It might be something really close to 5. And so we might be fooled into thinking that the limit's 5 when it's really something close to 5. Here's a really good example of that, right? So if you're looking for the limit as x approaches 1 of this function here, 3 to the x minus 3 over 5x minus 5, it turns out that that limit is this irrational number, this really weird irrational number, 3 times the natural log of 3 divided by 5. That number is approximately equal to 0.6592, okay? If you were to try to express the exact value of that limit using a chart or using a graph, you would not, and you would almost certainly not end up with this answer. So anyway, the point I'm trying to make is that we need to develop some kind of, I should say develop, but we need to develop some kind of algebraic technique for calculating limits, right? That's the only way to be absolutely certain about what a limit is. And we'll talk about that a little bit this semester. You'll talk about it in even more detail in calculus. But here's one thing that we should point out that's going to help us immediately, right? It's going to help us to calculate limits immediately. So the observation is this. If f of x is continuous on its domain, and if c is in the domain of f, then the limit as x approaches c of f of x is the same thing as the function value. So when we first started talking about limits, I said, well, sometimes the limit is the same thing as the function value and sometimes it's not. And I said we would have a better handle on when it is and when it isn't. Here's that fact, right? This is when the limit and the function value coincide. They coincide if the function is continuous. Now, what does it mean to be continuous? This is a huge topic that you'll cover in calculus. Excuse me. For now, suffice it to say that a function is continuous if it's a smooth function with no holes, no jumps, no asymptotes, okay? So something like this function on the first page is continuous. Something like this function is not continuous, right? It's discontinuous when x equals 4, all right? Which is why the function value and the limit do not coincide. Okay, so if you have any kind of discontinuity, like a hole or a jump or an asymptote or something like that, then the function value is not going to be the same thing as the limit, but otherwise it is the same, right? So in particular, whenever you're confronted with a limit, the first thing you should try is you should try to plug in the number. And if the number is the same thing, or sorry, if plugging in the number yields a real number as an output, then that real number is the limit. So for example, if we plug in 2 here, we get 5 times 2 squared minus 3 times 2 plus 4. 2 squared is 4. 4 times 5 is 20. So you get 18, right? That is the limit. That's the limit. Okay? You don't have to make any charts or look at any graphs. You can be confident that that is the limit of that function. Okay? And that happens anytime. Anytime you plug in this number and you get a number back out, right? That's just the limit. You may be thinking, well, but how could that possibly go wrong? Well, look at part B, right? If you try to do the same trick on part B, you try to plug in -2, you get 2 squared minus 3 times 2 plus 7 over 2 minus 2, and right away you run into a problem, right? Because now you've got 4 minus 6 plus 7 over 0, and this thing is undefined. Okay? That doesn't necessarily mean that the limit is undefined or that the limit does not exist. The limit might exist. This function might be approaching some finite value or maybe some infinite value, but the function value itself does not exist, right? So when this scenario happens, now your only choice is to use, well, your only choice for now is to use a chart or to look at a graph or something like that to find what the limit is. In calculus, you'll develop some really sophisticated techniques for determining algebraically what the limit of this function is, okay? But I'm just going to leave it at that. You know, it's like at this point you would make a table of values, right? See what value you're approaching. I'm not going to finish the problem. But part C, you'll notice, has the same issue, right? You try plugging in 2, you get a 0 in the denominator. I think what's different about part B and C is that in part B, if you actually work this out and try to figure out the limit, I think what you'll find in part B is that the limit does not exist, whereas in part C, the limit does exist. It'll approach some kind of finite value. So, but I'll leave that to you to kind of work out the details if you want. The moral of the story, though, is that when you're trying to calculate a limit, the very first thing you should do is just plug the number in and see if you get a value. And if you do, then that's the limit, right? If you try plugging the number in and you get something undefined, well, then you have some more work to do, right? You have to make a table or look at a graph or something like that in order to figure out what the limit is. At least for now, right? That's the best that we're going to be able to do. So that'll do it for this section. Kind of a long one, but thank you for tuning in. We'll see you in the next one.